For exercise 10, we're going to change it up just a little bit. We still have the exact same base shape in between these two curves here with our representative rectangle, but this time the volume of our solid is going to be formed by semicircular cross sections, once again perpendicular to the x-axis. So imagine, if you will, that the distance between these 2 points in between that line and the parabola, this time is going to become the diameter of a semicircular cross section. And here's what that image might look like. All right, so in order to find the volume of this, so think of it as it's kind of it's half a semicircular cylinder, I guess, maybe half a cylinder, right? So to find its volume, you need to find the area of a semicircle and then multiply it times its width. So to find the area of a semicircle, we need the radius here. We have the diameter, so we're going to have to take half of that diameter in order to find the radius. The diameter length is top minus bottom once again, which is our g of x minus our f of x. We're just going to take half of it so that we can have the radius length there. And then I'm pretty sure still we have a delta x for our width. Let's put these things together with the area formula for a semicircle in order to find the volume of the shape, and then we'll take a look at what this three-dimensional solid would look like. Okay, so do I have enough space down here to do? No, so I'll have to work up above. Okay, so to find the area of a semicircle, its formula, of course, would be equal to 1/2 pi r squared. Now the 1/2 that's in this formula is not the same 1/2 that's inside of this 1/2 g of x minus f of x. That's just so that we could find the length of the radius given the diameter, right? So let's set up this definite integral. So just like before, same limits of integration from -1 to 2, right? And then we were gonna just basically form this formula here. So I have 1/2 pi multiplied times our radius squared. And our radius is the function 1/2 of g of x minus f of x, a whole bunch of parentheses and brackets up in here. All of this thing being squared, right? So this is our radius basically squared. R squared. Yep. Okay. No. Yes. And then with respect to x. Let me rewrite this just a little bit so you can see how it compares to the previous one that we did. So it's going to be super unconventional. I'm going to go up instead of down. For example, I'm going to take this 1/2 pi, just bringing it to the outside as a pi over 2. Right? And then I can square the stuff that's inside of here. So I'm going to square the 1/2. That's going to make it a 1/4. And then I'm going to have my g of x minus my f of x squared. Right? And then maybe one more simplification. I'll take this 1/4 out to meet that pi over 2. So we have a final answer of pi over 8, definite integral, -1 to 2 of g of x minus our f of x squared. Now notice that the integral itself is exactly the same as the one for the square. There it is. There's the one for the square. It's just that this one lacks the scalar of pi over 8, which is basically going to make that the volume of those semicircular pieces. Let's see what this thing is going to look like, huh? I'm actually going to build this one with you. If you wanted to watch this one at 14,000 times speed, that's probably sound like a wise advice here. All right, so here is our base shape. Get that thing in focus. Yep, that looks good. All right, and then here's all my little cross-sectional pieces. Don't lose one. There we go. That's number 11. All right, so you can see here, here's one of my little pieces. The diameter of this, that's going to be the distance between the 2 points, 2 corresponding points on my 2 functions here. I'm just going to fit this in here. Okay, don't drink too much coffee before you do these little models. Yeah, all right, there's a pro tip. Okay, I didn't drink coffee, I just had lots of caffeine though. Oh, okay. Because who doesn't love caffeine? All right, so there's the second one. Look, this is starting to come together. All right, again, diameter. Diameter is going to change as the distance between those 2 functions changes. It's the third one. There we go. Oh yeah, let's see how fast I can do this. I'll pick up the pace. It fits in there very nicely, doesn't it? Oh, this one's off a little bit. And it's beginning to look sort of like, I'm going to say a croissant, right? This is a French pastry. Number 11. No, 10 comes before 11 when we count. Mr. Noel. Okay, there we go. That fits in there perfectly. And then we have one more. Don't worry, this is the only one I'm going to do this for you. I'll just have the model built the next time. Okay, look at that. Oh, in all of its glory.